So one of the joys of being able to do a double act is that we can arrange this kind of mildly dramatic happenings in which one of us gets into trouble and the other one fixes it. So I'm now going to get into trouble. Okay, so here's a thing that lives in a Haskell library. Dare I actually open up GHCI in another buffer?
Yes, maybe.
Or actually in terminal window, you can make the big font. Yes, okay. GHCI. Okay, so the thing we want to write next is the function that projects an element out of a list. So in Haskell, strings are lists of characters. So if I say what's in position 3, then I get the K because we count from 0. So it's the number is how many to skip before the one that you want. But the type of bang bang is list of A to int to A. And you know, that's blatantly a lie. And we'll see that if I say Haskell, but I try and project out the 12th element. You know, runtime error. You know, they say well-typed programs don't go wrong, but what the hell's that? I mean, you have to work quite hard to explain why that's a kind of going wrong that doesn't matter. I mean, the other giveaway, of course, is that we're perfectly entitled to feed in the empty list. And how are we going to get an A out? we don't even know what A is. Anyway, so that's the state of things in Haskell.
Well, is int natural numbers or is it?
Neither. Int is signed integers that fit in a machine word. There is also a type of called integer in Haskell, which is uses GNU multi-precision to allow arbitrarily large integers. But yes, in particular, I can certainly ask for I can never remember what yeah. I'll do the way I know works. Right. Yes. You know. Okay. So bad news. Let's see what happens when we try and do the same thing in Agda. So let's set myself up. I've got. I want. So here's a bit more notation. So here, this for all allows me to give the input types in a slightly different format. And in particular, it allows me to write an implicit argument, just to name a bunch of implicit arguments with the idea that Agda is going to figure out from the fact that I've used A as an element type in a list, that A has to be a type, that A has to live in set. So I can tell Agda, oh, you figure out the type of this thing, use what constraints are available to figure that out. So that notation means exactly the same thing as, okay, one of these things, but with A instead of X.
And an underscore instead of set.
Oh. I'm always in danger of clicking things that I don't intend to. Okay, so our business is to explain how to project out the element of the list so the element of x's that is in position n. You can see, oh, can I make, what's the best way to make the font bigger in the...
I'll do it.
Yeah. I mean, not in that buffer, in the other buffer.
The buffer.
It's the information that is too tiny. I mean, either that, or I'll have to switch to my reading glasses to look at the context. Yes.
Maybe that's too big, but
That's fine. That's good. Okay. So you can see if I do Control-C, Control-comma, that there's a set A not in scope. So it has figured out that A is supposed to be a set. We've got a list of A's. We've got a number. We know the number is not negative, but that may not help much. And we have to figure out how to make progress. Okay, so
should we take a quick look at what the natural numbers are, maybe?
Oh,
we haven't seen them before.
Okay, sure. Is there
that means I middle click, I guess.
What,
so
what is middle click?
It's the middle. So if you have a mouse which has a middle mouse button, and if you middle click on any definition, it will take you to its definition. So this is in a built-in file.
Yes. So the natural numbers are defined by counting, right? 0 gives you a natural number, and taking the successor of an old natural number makes a new one. Okay. Through the years, great wars have been fought as to whether the natural numbers start at 0 or at 1. They start at 0. And other wars have been fought about how many C's should be in suck for successor, and the correct answer is 1. But
let's go back.
But yeah, anyway. We're going to try and figure out how to define this. And we got, I mean, it's the usual deal. We have to ask ourselves, can we see enough to say what the output is? And no, we can't.
And not only because your shadow is in the goal.
Yes. Okay. We can't see enough to say what the output is. So we should start looking. We have a free choice of which to look at, right? Should we look at the list or shall we look at the number?
List.
So I'm going to look at the list. So you saw me type X's into the hole and then hit Control-C, Control-C. So you'll find that Fred always hits Control-C, Control-C, and then types the variable name in the mini buffer. I always type the variable name in the hole and then hit Control-C, Control-C. Let 1,000 flowers bloom. Okay, so let's put the nil case off for a moment. Right. In the case where where our list is X cons X's, we now have a dilemma. We need to figure out, is the answer the X or is it one of the X's? I mean, there's a pretty good way to figure out which of those situations we're in, and that's to look at the number. So we look at the number. Great. If we want the thing in position 0, then what is it? It's X. And if we want the thing that is in position suck n in X cons X's,
Excess.
Yeah, so we that's the thing. We peel one element off the list, we peel one suck off the number, and we keep going. I just keep doing the it's off by one error for finding your control key. Okay, so we're doing pretty well in the cons case. But now we are faced with a rather different problem in the nil case. Okay, we have at our disposal a number, though goodness knows what good it will do us. There is some arbitrary unknown type, A, and we are being asked to produce an element of this type that we don't even know. This is a difficult problem. I mean, and if we look at the type, it's because the type is making a promise that we can't deliver on. It says, you give me a list of things and I'll give you a thing for any type of thing. We're always free to shove in the empty list and say, where's my element? Make up an element of this type. Right, you know, that's just magical thinking. Haskell deals with it by just having a runtime error. We're not allowed. I could, you know, comment out this case and reload the file, and then Agda moans, hang on a minute, what about this business here? You know, you're missing some stuff.
Every type is there empty type.
So no, some types have no things in them. Yeah, that's well, we'll come back to that. That's it's profound that some types are empty, SOME types. There are such things as empty types, and we use that to make bad things impossible. I mean, this is how we actually do some logic in our situation. All right, so I'm in trouble. I know, you know, not only am I too stupid to fill in this hole, I'm sufficiently non-stupid to know that there's no way to fill in this hole just by thinking, you know, we don't know anything about the type A, so there's nothing we can do. There's no chance. So I've got us into trouble. You know,
Right, let's see.
how do we say something? We're in trouble because we said something false.
Yeah, so we're claiming we can always get an A out, right? So sorry if we are really hammering this point. But that's not true, because A could be empty and then,
Oh, hang on. Yeah. Is it my go?
Yeah, but should we swap? Or
Up to you.
yeah, let's swap maybe. So Connor here had an idea how to fix this, but I'm now going to present. So the problem indeed is that we're always saying we'll return an A, right? But we can't always return an A. So the Haskell way to do this would be to return maybe an A instead, right? So we have a way to get out of trouble if we need it. So we can do exactly the same thing in Agda. If I just open this maybe file, we can take a look at it. There's a base version. You have to go hunting sometimes. There's a built-in version. And then finally, here's the definition of maybe. And it looks similar to the Haskell definition, right? Except there is this Agda syntax instead. And make it bigger.
Yeah.
And you see the constructors don't start with a capital letter because they don't have to in Agda. So, and there's this this little set A thing here, which might be confusing. So set, we said, was the type of types, right? But these are stratified. So there's a set 0 and a set 1 and a set 2, because that way we can avoid the paradox of the barber that always shaves everyone who doesn't shave themselves.
Yeah, there's a whole, I think that's a distraction at this
Yes,
stage.
you're right, you're right.
But one way of thinking about it is that when we write set with no number, we mean set 0. Set 0 is the type of boring types that are just full of stuff that never talk about that don't talk about types themselves. And then set 1 is the type of types that talk about types in set 0.
That's right. So the point here with the maybe is that this maybe type lives in any set A. So it's quantified over all A's here.
Is A a natural number?
A is a so-called level, but it's basically a natural number. Yeah. Right. So the important point is that if A is some kind of set, then maybe of A is some kind of set, and it has 2 constructors, right? Just and nothing.
Yes. So in particular, if we think of A as level 0, then it's the same deal as when we wrote lists. There's an element type, and we get either just or nothing. So yeah, so here's it's good to comment out and copy.
Comment out this one.
And
I'll copy it here. And I said, rather than saying I'm going to return an A, I'm going to return maybe an A.
So here we are making a weaker promise that we hope we can keep by slackening off the demand for what the output is.
Okay, and then we can basically proceed the same way as before, right? So I'm going to start by pattern matching on X's. And then,
This does break your sort of, you want everything to know that it's going to finish, doesn't it?
It's going to finish.
I mean, yeah, it's not. Okay.
Yeah.
well, sometimes it's going to return the nothing constructor.
Yeah, fine.
Yes.
But that's a thing, right?
Yes.
Yeah.
So instead of the program just going wrong, it's allowed to return the I went wrong value. You know.
Okay, so so here, before we just returned X, but we see that, so here I did Control-C, Control full stop to see the type of the thing I have in the goal. So I see that X is an A, but I want a maybe A here, right? So I have to remember that now I have to be more explicit. I can't just return A, I have to return just A, if you pardon the pun. So I do just A, just X, then that's a maybe A, and I can return that, right? And in the recursive call here, I wanted to do X's lookup N, and that's going to give me a maybe N again, so I can just do that recursive call. So this is the same as before, right? I just put in a just in front of the final return value. And then here, where we said that I couldn't do anything sensible, I'm now free to just return nothing, right?
Why is it undisplaying 2020?
Right, so that's a good question. And the reason is that the type of nothing is maybe A for any A, right? Maybe X for any X.
Yeah.
So when I'm asking for the type of nothing, Agda hasn't figured out which X I want. So it's printing a meta variable here.
Okay.
Yes.
And then when I give it in the whole, it's going to say, well, the only X that will work is if X is equal to this A. And the type is.
So it figures out that the thing it doesn't know has to be the thing that we want.
Could you put that, is there a way to put that explicitly?
Oh yeah.
Yeah, so I could say A equals A,
You
except
need
that
to
then
bring A into scope.
I have to
yes.
bring into scope. So let's maybe not get distracted by that now.
Yes. We will teach you how to do kind of manual override on things which are usually left implicit soon enough. It's often the case that we need to make things explicitly visible when we're defining stuff, but we can leave them implicit at use sites. That's quite typical.
Which indeed is what's happening with this A here. But we're not. Well, we don't need it here either. Okay, so that's how you would do it in Haskell.
Yes.
And that's great, right? Except that now, like maybe you alluded to, this is quite annoying to use in practice, right?
Yeah.
Because if you now want to look up the third position in the list Haskell, then you can't just do that. You have to pattern match on the result to see if it's nothing or just. Right?
Yeah, we have kind of legitimized failure by adding it as a value, but now we have to worry about whether the value we got was failure, even though we're doing something that ought to work. You know, the whole point is that we never want this to fail. So instead of slackening the output type, we might be able to make a better promise that we can keep by tightening the input type.
Yeah, why don't you try and do that?
Do you want me to load Vec and Fin from libraries, or do you want me to
we could invent them also.
invent them? Okay. So the problem is, or we get into trouble when our natural number is longer, or is bigger than the length of the list. It's the length of the list or more, right? So there's a range of numbers that are okay, and we figure out what that range is if we know the length of the list. So maybe lengths of lists are important sometimes. In particular, what we're dealing with is a situation where there's a hidden connection between the kind of meaningfulness of the list and the meaningfulness of the number. There's a relationship that we're not being explicit about that we need to hold. And correspondingly, you know, we're dealing with situations, we end up in situations that shouldn't happen because we've been inarticulate about what ought to make sense. Okay, so let me go and grab this now. I've got to play how does Fred's computer work. I think I can do it the old-fashioned way. Right. So, judging by the types that we've got knocking around, I'm going to manufacture a refinement of our notion of list that makes explicit what the length of the list is. And in the trade, this is known, this type tends to be called vec, although some people want it to be called vect. For vectors, so the idea is that a vector is a list indexed by its length. So let me show you how that goes.
Sorry, it's a Unicode. NAT.
Oh, it's a Unicode NAT.
Slash B, capital M. Lowercase b, yeah.
Okay, thanks. I'm probably going to need that, either that or copy paste. Okay. So, so what just happened is that I introduced an extra argument of vec to the right of the colon. I didn't give it a name. So it's not in scope, but I'm saying that vec takes a set and a number and gives you a set. So it takes an element type and a number that's going to be the length, and it gives you back the set of lists of elements that are of length exactly the number. So I have to fix up the definition to make that happen. And what's the key distinction between things that live left of the colon and right of the colon is that things left of the colon are in scope for the whole of the data declaration. And as we saw last time, they have to be used. If I have X here, I have to have X here, X here, X here. I'm defining vec X. But the things that are right of the colon, I am free to choose specific natural numbers for the return types of each of the constructors and in the recursive positions. So in particular, I'm free to say that nil makes not a vec x of any length, but specifically a vec x0. So I'm saying nil is the vector of length 0. And then I'm just by way of showing the variations and also by way of being a Luddite, I'm going to type for all as an ASCII. Actually, does it work if I say / for all? Oh, it does. See, I'm learning. For all n, if we have an element at the head and a tail whose length is n, then the whole vector that we make with cons has length suc n. Okay, and Agda is happy with that definition. One thing you'll notice from that's different from Haskell is that I've just reused nil and cons. List is still in scope with constructors nil and cons, and I've now brought vectors into scope with constructors nil and cons. Agda is smart enough to figure out which constructor is which from which type you're trying to manufacture. So it resolves the ambiguity using the type information available. And if it can't, it'll moan.
But it only works for constructors. It doesn't work for functions.
For constructors in general, the expectation is that when you're building some data, you will know the type of the data that you're building and correspondingly be able to figure out which constructors are available. Okay, so now we've got vectors that where we're managing the length in the type. The other thing we need to figure out is how to manage that the number is in range. So we're going to need a type of numbers less than a given n, right? We need a number that's less than the length, right? In order to look up the thing in that position. So let's write the type of numbers less than n, and in the trade this tends to be called fin. Should I just do it? It's in a library somewhere.
Let's do it, I think.
And do we still have I keep hitting things badly. No, we don't have I was going to go and fetch nat. Maybe I'll do it like in, because I can type the definition of natural numbers in my sleep. This is the definition of natural numbers, which I'm reproducing in order to perform the same sort of transformation. So the idea is I'm going to refine the definition of natural numbers so that so that we acquire an upper bound on them. So here goes. First of all, I'm going to change the name to fin. 1, 2, 3, 4. And then I'm going to say that fin lives in nat arrow set.
\bm.
Okay, yes. All right. And then we have to think. So the idea is that the number in the type is strictly bigger than all of the values available. So that's to say, fin n is the numbers strictly less than n. Okay, so which numbers is 0 strictly less than? Well, is
Like none of them.
well, so 0 is not strictly less than 0. I mean, think about it this way: if our list's length is 0, do we want to be able to look up the thing in position 0? No, we'd be in trouble. But if there's at least one thing in the list, then it has a position 0. Okay, cool. Okay, so we know that if our upper bound is at least 1, then 0 definitely fits. Okay, now what about successors? We could there are various ways we could do this, but so you could think, so successor is going to give us a number that's at least 1, which means the length had better be at least 2. So as a first approximation, we could say for all n, we want to make a number that's at least 2, so that's suck n for some n, in which case, what do we want to put here? If the successor is at least 2, then what's the predecessor? Yeah, this would be suck n. So this is okay. Oh, whoops, that was okay. I've done the thing again. I wish I stopped doing that. And some stupid.
There's something in.
Oh, yeah. Okay, so this is fine, but I'm going to do what we sometimes call golfing. How do I get rid of this red lump?
You delete the white space that you put in.
Okay. So one thing we notice about this definition, can you see any way to construct a value in fin 0? No, fin 0 is empty. And that's just as well, because that's going to get us out of trouble when our vector is nil. The fact that there are no valid places to look up is going to mean we have a way of winning. But it also means that it's harmless for me to generalize this type very slightly. By saying, oh, well, you can have a successor index, a successor value in fin of 1 plus something if you've got, if you're taking the successor of something in fin n. So yeah, so this basically says, if I know a number that's already below n, I can take its successor and make a number below suck n. And in the case where n is 0, so that's to say, can I use suck to make a value in fin 1? Well, I can try, but that will, when I do, well, let's just, instead of talking about it, let's try. I guess does Agda let me use?
You can
Right.
just say one. Yes.
Yes, the library natural numbers are specially hacked so that you can write numbers in decimal instead of saying suck, 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 suck a lot. Okay. Right. So now that I've made my little adjustment, my optimization, I am allowed to start making my element of fin1 by saying suck of something. But now I'm faced with the problem of making a value in fin0. So don't worry, by relaxing, by making the type of suck of this thing less fussy, I haven't caused any extra bogus numbers to be thrown in anywhere.
And I can tell the fin0 is empty.
That's an excellent question. Let's find out. Okay, so we want to write, I guess I want to do this thing again. Actually, what I'm going to do is I'm going to steal the old one. Okay, but now my type is going to be for all a and n, vec a n to fin n to a. Okay, I'm just going to be wild and reload this program. Okay, everything that was supposed to work still works, right? But something, maybe I should rewind or, well, okay. I'll show you that stuff in a moment. Let's finish the job. Let's look at our problem. We're back in the dilemma we were in, where our list is empty and we have some index. Let's look at the problem that we are in. There's some type we don't know, so there's no way we're actually going to be able to pick an element that goes here. But our n, instead of being an arbitrary natural number, is an element of fin0. And we know there's no such thing. So Jake's question, can Agda tell that there's no such thing as a fin0, becomes a very important question. Let's see what happens if we attempt to do a case split on n. What just happened? Well, one thing happened is that there's no equal sign. And another thing that happened is that this empty set of parentheses appeared in a pattern. So this is a left-hand side with empty parens in a position in the pattern. And what that means in Agda, to confuse Haskell programmers, is the empty set of parens points out the place where something can't possibly exist. So instead of solving this problem by giving an output, we are solving this problem by pointing out that an input is bullshit.
Is that the same as saying
Yes.
quite data?
Yeah, we are saying, this can't be happening to me, get me out of here. So that's one marvelous thing that you get in Agda that you don't get in many other programming languages is, you know, the ability to push back against somebody who's lying to you, right? Someone who claims to be giving you a position inside for an element in the empty list is telling you a lie. And this is us calling them on it. So that's kind of fun that sometimes there's two ways out. You either give an answer or you explain why the situation's impossible. And that's what we just did. We just ruled out the possibility of having a position in a vector of length 0. So yeah, so what Agda's literally doing is it's saying I've got I'm checking out I'm trying to split fin 0 into constructor possibilities. So I go and look at the definition of fin, and I see that there's a constructor that makes fin when the length or when its index is a suck, but suck is not 0. And likewise, the other one is also making something in a suck, but suck is not 0. Okay, so this is a key thing, a key sort of reasoning principle that you have to get your head around, which is that Agda knows that different constructors of a given data type cannot possibly make the same value. So, so what is the reasoning here is that both constructors are ruled out for fin 0 because 0 is not suck of anything. So Agda, when you do k-split, Agda is actually not just listing the constructors that are mentioned in the declaration of the type. It's doing a filter. It's giving you just the ones that are possible. And here it's figuring out that they're all impossible and saying, fine, job done, you win.
Is that implicit in the definition of a type that you can't have constructors the same value?
Yes. So when you have a data type, you declare, so it's again, it's the operative word is generative. You're creating a bunch of different constructors, and because the constructors are different, they construct different things.
I mean, you can also see that when you do a pattern matching definition like this, it's clear that 0 cannot be the same as suck because you're given two different answers for 0 and suck, right? So
yeah,
it wouldn't make
in more general cases.
It wouldn't make sense, but yes, in general, constructors are always different.
Okay. So,
If
yes.
you ran like that function on an empty set, an empty list, how would it handle it?
Well,
It's just not letting you handle it at all. Wouldn't like compile, I guess.
well, it could happen hypothetically.
Yeah.
So yeah, if you want to just write a test case, then in order to come up with your test case, if you want nil project, nil bang bang something, then you, in order to construct your test case, have to come up with a value in fin 0. Ain't gonna happen. And you could be in a situation where you were in some funny context where you had a variable of type fin 0. So yeah, you're in an impossible hypothetical situation, but variables aren't constructors. So when you compute with things that aren't actually values, it's okay to get stuck. Yeah, so you could say, can you reduce nil project x for some hypothetical x in fin 0? The machine will just say, I don't know how to reduce that. Maybe if you told me what x was, I'd be able to have a better go. Aha! That's how you know.
I mean, one way to think about it is there is no equation that talks about nil project x, right? It's not one of these because this is not nil and there is no x here. So they will just get stuck. There's no equation that tells you what to do.
Yeah.
So if you load this down, it'll just be fine.
Yeah, it's already
It's
good.
loaded.
Oh, is it already loaded? Right.
All done.
It's all done.
And can you also get rid of the empty type declaration bit? That coordination. Can you get rid of the nil aspect?
This one,
I think you can, right?
I think you can, but only because our friend Guillaume is very clever. Yeah, it's okay to, it's happy with you leaving that one out, but I would actually rather it was put in.
So what's happening is it's checking, are there any missing cases? And they say, okay, you haven't said what to do with nil in the first position. And then it checks, is this a possible case? And it realizes, no, it's not possible because there's a fin 0 here. And then it says, okay, it's okay to leave it out.
Okay. I think we should do
we do fine. Yeah.
Find. Yeah. There's some stuff that I didn't do that development very interactively. There's a thing that you, but I think we'll see.
Yeah.
We'll see some more stuff.
Right. So we wanted to give you one more example just to help you a little bit for the coursework as well. So the idea here is a different version that talks about vectors and fins, but this time we are given a function which tells you if we have a good element or not, right? So it's a function from elements to booleans. So it's going to return true or false, and a vector of length n. And we maybe want to find a position where this element, where a good element is in the vector, right?
Yes. So
operationally, sorry.
Yeah. So the specification is find the first thing in the vector that passes the test.
Yeah.
And if we're lucky, we will return a position, which we know is a position in the vector. If there's no such element, then we're free to return nothing. One could imagine tightening this type some more.
Yeah. So we already know that if we return just something, then that's going to be definitely some position in the vector because it's a fin n, so it's within the length of the vector.
So the promise that we're making out loud, but not explicitly, is that if this gives you back just n, or just I for some index I, then projecting the thing in position I from the vector will give something that passes the test.
But it's not as tight as it could be, because I could, for example, always return nothing here, right?
Yeah.
But I'm not going to do that. So, okay, so I take P, which is my predicate, P for predicate, which tells me if I like it, the element or not, and I take my vector. And then what can I possibly do except?
Well, have a look at the goal, have a look at the context, Fred. It's important. Right, so at the moment, we know that we want a fin n and our vector has length n. That's to say, we haven't looked at anything yet, so we don't know anything about the length of the vector.
But now I'm going to look at the vector, right? Because that's the only thing I can really do here. So I'm pattern matching. I get a nil case and a const case. So here, we see that the vector has disappeared because we know it's nil. And the goal now says we have to produce a fin 0. Or maybe fin 0, right? Because the length of the vector was 0. And because it's the same n here and here, that means that when the vector becomes nil, then the length becomes 0, which propagates here. Right?
Yeah, so this is the thing that didn't happen in Haskell because types of things weren't related to each other. Here we're in a situation where you can look at one thing and learn a bunch of stuff about other things because they're related by the same thing, this n showing up in this place here in the return type. So when we look at one input, the return type gets tighter because we've learned more.
So it's telling us what to do in this case, right? Because we have a choice of nothing or just something. But if I say just something, I have to produce something in fin 0, which we have said was impossible.
So yeah,
so
that
here
better
I
be
am
nothing.
Forced to do this move. So
Okay.
And afterwards, that automatically auto mode, I assume.
Yes.
Yes, I guess so. Yeah. Okay, so let's look at the other case. So here now I had a cons, so I had a list of at least length m plus 1, exactly m plus 1, which means I have to produce a fin suck n as well, right? And now I have an element, so I can use my p to see if it's good or not, right? If I do p of x, that's going to give me a Boolean. But now I would like to look at this Boolean and see if it's actually true or false. Right? So this is something you might find useful for the coursework as well. So one way to do that is to say, okay, I want to pattern match on this additional thing, right? Here I've been pattern matching on things I've been given as arguments, but now I want to pattern match on this expression. And I can do that if I say with, then the expression, then I copy everything.
You'll
or
need a space.
yes, that's the expression I want. Okay, I copy everything from above. Sometimes you can get away with saying dot, dot, dot instead. But let's just copy it. I do a parallel bar, and then here I have a new variable that I can pattern match on. I like using Q for this for some reason.
You'll need to get rid of your old.
And I have to get rid of this.
Right.
So if I now look here, I see that I have one more variable in scope, which is this QQQQ, which represents the value of this expression. And I can now pattern match on this like anything else. Right. If I do that.
Yeah, so we just added a sort of extra column to the collection of things we're inspecting.
So now I can say, okay, if this is false, then I want to do something. If this is true, I want to do something. Let's do the true case first. Because if it's true, then I found the position I wanted, right? So in this case, I can say just of something. And what is my position? Well, here it's the head of the list, right? That's position 0. And thankfully, 0, if I just ask for the type of 0, I'm just going to get, well, I don't know what it is because there's many different zeros in scope, right? So if I want to be precise, I can say, well, I want a fin 0. We see that fin 0 has type suck of something for any something. That's what I want in this case.
Would you have to write fin 0?
No, you don't.
No, so now I delete it again.
Yeah.
But
no, when it's clear that it's demanding a fin, then that's a pretty good steer, which 0.
okay, so what about this case? So here my P said, okay, this one was not good. That means I should keep looking in the rest of the list, right? So I could try to do find P x's, and if I look at the type of this, I see that that will maybe give me an index, but now the lengths here are not quite right anymore, right? Because I wanted to return a position in my original list, which has length m+1, but if I keep looking, then I will get the position in just the tail. So position in the tail should be the same thing as the position in the whole list +1, right? Because I skipped past the first element. So I'm going to do another with on this. This. Okay, and then I can pattern match on that result. And it's either going to be just of something or nothing. If it was nothing, that means that the whole thing failed. And I basically have no choice but to say that I'm going to fail as well, right? So the recursive call failed, we didn't find it anywhere. That means it wasn't in the first position, it wasn't in the rest of it. So we just have to return nothing. And if we found a K, well, then we should be happy and rejoice. But the problem was that the K was a fin n and we wanted a fin suck n, right?
Yeah, well, we know we're not in position 0.
So if we add 1 to this, that's going to give us the overall position because it was position K in the tail, and now we're skipping past 1 more, right? So that's suck K.
It's traditional to use K absent-mindedly and then realize that you've said something funny. Yeah. So what's going on here? Remember, we said looking at something. We had examples. Looking at the vector affected the types of other stuff. So it's also the case that looking at stuff in an extra column added by a with can impact on all the things you're analyzing, as well as on the return type. So that's why we don't have things like case statements. So the case expression in Haskell is appropriate for looking at one thing independently of everything else to decide how to proceed. But now we're in a situation where everything's potentially interrelated. And looking at one thing might cause learning about other things. So instead, you should think of having a bunch of things you're currently analyzing. And you can pick any one of them and get more information about it. And if there's something extra that you don't yet have in your hand to analyze, width is how you get your hands on it. Yeah. So instead of saying, let's go over to the right-hand side so I can do case on some other expression, we say, let's bring the other expression's value to the left-hand side so we can carry on doing whatever analysis we want. You find an awful lot of the time, the art of programming in Agda is to stay working on the left of the equal sign for as long as possible until you're ready to commit to an answer.
Okay, so we are already past the time.
Oh, yeah, we should.
Are there any burning questions?
Class potentially stupid.
Yes. Do you want the whole class to hear your stupid question?
I don't care. The width, is it not just a fancy if then else on the left hand? As it is it equivalent to if then else on the left hand, on the right hand?
Well, yeah, you could certainly, if you choose width and that your value happens to be a Boolean, then sure. But here we used it for maybe. I mean, it's just you can, you know, anything you can pattern match on. I mean, actually, you don't even have to be able to pattern match on it. You get your hands on anything, and if it so happens you can pattern match on it, then you can, you know, keep going.
It's pattern matching on an expression, right?
Yeah. So the idea is that we kind of introduce a new column header, and then we've got a column of values for it. So we're kind of tabulating the inputs and then the extra stuff that we ask for, depending on what trouble we get into. Right, we should shut up.
Yes.
It's a full